The next speaker is Gro Markeset. Please, the floor is yours.
Thank you. I've been mentioned several times this investigation of an existing structure. So I will go through this inspection and measurements. And as Carmen said, it is based on investigation and measurements performed on the marine quay structure in Norway. And it is also referred into the paper listed below. And I also go into some inspection of Norwegian bridges, also discussing this issue. I will also say something about the definition of critical chloride content. It's mentioned by several speakers, but this Ccrit is defined in different ways. It could be the chloride content required for depassivation of the reinforcement surface, or it could be the chloride content associated with some sign of surface corrosion. And of course, this will give different results if you follow the first or the second definition. And as mentioned also, FIB Model Code for Service Life Design has this definition: the total chloride content which leads to the depassivation of the reinforcement surface and initiation of iron dissolution, irrespective of whether it leads to visible corrosion damage on the concrete surface. So this we need to have in mind when we are discussing the chloride content and the value of it. So I will go into the investigations or the determination of the Ccrit in this quay structure. Is shown below this structure here. It's rather large quay structure in the fjord up in the north of Norway. And in that structure, we installed corrosion sensors in the splash zone. At that time, the structure was 37 years old. And we found out by testing in the laboratory based on core samples that the concrete was a coarse grained Portland cement with a water cement ratio varying between 0.4 and 0.5. And indicated here, when we drill out for the corrosion sensor installations, we have coarse 50 millimeter in diameter, where we could perform chloride profiles as illustrated here. So then we know the chloride profiles in different locations of the structure. And what did we use? Yes, it was corrosion sensor, which is called expansion Ring-Anode System, which is illustrated to the right, where we have measuring rings or expansion ring anodes. This is 6 of them with a distance of 10 millimeter between each of them. And those different rings could then be linked to a coated dynamic pin. And using a microampermeter, we could measure the corrosion current in different intervals illustrated here. So that is the principle of the expansion Ring-Anode System. And a new illustration of how we did this measurement. We have the concrete surface here, and then we drilled out the space for the corrosion ring illustrated here. So we drilled out holes with a diameter of about 50 millimeter. Then for those concrete cores was where we measured the chloride profiles, sent them to laboratory, of course, and then we installed the expansion ring anode, so this corrosion sensor system, and they were twisted, so they were really fit into the structure. And by removing the protection cap, it could be installed measurements that could read the electrical current or other signals. And here showing what we could measure. This is the electrical current. Could have this corrosion potential, the voltage here, and also the resistance of the concrete and the temperature, depending on when we are measuring. Here is illustrated day 2, 4, 6, and 8, and 10. And then we use this data to evaluate the activity of exceeding the depassivation of the corrosion situation in each location. So here is the situation, what we can read from the corrosion measurements, and then we try to compare the signals we obtained from the corrosion rings with the chloride profiles from the same area where we have drilled out the concrete, of course. So if you have a signal, let us say here, then we can go in and find what is the chloride content in that area. So that's the system where we are finding the corrosion current and the critical or the chloride content in that situation, and then find what the critical chloride will be. So then we could then use distribution from all the measurements, find the probability of corrosion, because we can't say 100% each place that this is corrosion, but it's a probability of corrosion. It's a lot of uncertainties and variations both in the measurements and also the variation in the environment in the system. So when we interpreted the results, we find those areas where we have measurements. We have we installed 14 corrosion sensors. 2 of them were broken, so we had 12 we could investigate. So when we fit the data with this log normal curve, we could, so this blue continuous line is a fitted curve, and the measurements of the data is here. So in this situation, we had a log normal distribution with a mean value of 0.77 with a coefficient of variation of 32. And this is compared to fib model code showing here, showing several times also by Carmen. So it's not far from what is suggested in the fib model code, but those tests or examples they were used in fib model code is, I think they were mainly from laboratory tests. And this, of course, is then obtained from one concrete structure, will have one the same concrete type and water cement ratio in the whole structure. So this is what we found on these key structures. But if we go into another way of try to find the critical chloride in existing structure, we can go and look into what I found in some marine breaches in Norway. Then they perform a visual inspection of the reinforcement after chiseling and combined with chloride measurements. So they measure the chloride content at the reinforcement. And then they use an evaluation, which is typical when you identified some corrosion problems maybe in the reinforcement. Then they you have a visual inspection of the reinforcement and use a known sign of corrosion called A. It could be a corrosion level B, signs indicating deposition, or corrosion level C, sign of surface corrosion, and corrosion level D, heavy corrosion, and E, severe corrosion and pitting. So this is a typical system often used in inspection of existing breaches. So if you use this system here and combine them with chloride measurements, the Norwegian Public Road Administration found this kind of results. They have one large bridge where they perform a lot of inspection and chloride measurements, this blue Gimsøstraumen bridge, and then they have other structures with this red one here. And then you can see again this A, corrosion level A, is no corrosion, and B, start deposition. C, you have this some surface corrosion, heavy corrosion, and heavy corrosion with pitting. So then we can say, what is the critical chloride content for onset of corrosion? Is it when we have start deposition and we don't see any iron dissolution maybe, but we have an indication of there's something going on, and you have where we have some maybe small rust stain, and there you see, okay, here for sure there is some corrosion, but it's not heavy. And if we look into this situation, we can see that this Gimsøstraumen bridge, this blue one, they have a mean value of the critical chloride content here of 0.12 of the concrete mass, but that corresponds to 0.76% of chloride of the cement weight. So that is very close to the situation based on what we found in the key structure, 0.77. So it seems that that type of breaches and the key structure in the more or less the same environment situation, the onset of corrosion was rather similar, 0.77 or 0.76 here. So what can we use those information in real structure, or say anything about service life? Because if you know what the critical chloride content is in the existing structure, you should use the values for something in the future. So if we are trying to calculate the service life or the needed concrete cover to reach service life of 50 or 100 years, it's we often use fixed cycle over diffusion, giving it this way. I will not say too much about it, but it's fixed second law, and then we have some parameters where we include the type dependency of the diffusion, this aging factor alpha. So then if we are starting to calculate this service life, we need information about all the parameters, where this x is the distance from the surface of the structure, and that are the parameter we calculate to reach a certain service life. We need the chloride surface concentration that can be found from existing structures. We need the diffusion coefficients that we know about the normal value for different kind of concrete types. And we need, of course, a reference period that it's, if it's 50 years, or which is typical for a key structure, or 100 years, or 110, or whatever, 300 if it's needed for bridge structures. And this aging factor, because this time, this chloride diffusion coefficient is time dependent. And I will not go too much into it, but there was a discussion of this parameter. Is it the same through all the years, or is it decreasing? And then we have the limit for corrosion initiation, this 2D model, where we reach the critical chloride content. What we are talking about here, we need reliable values. So we can say, here's the end of the service life, or here's the end of the life before we start having corrosion of the reinforcement. So if we try to calculate what is needed of concrete cover, if you have, for instance, 50 or 100 years service life, we can have input parameters as illustrated here. This is typical value of the surface, the chloride surface concentration, at least found in a lot of, based on a lot of quays and bridges in Norway. Here is the uncertain value of the needed cover to the reinforcement to reach the service life expected. And then we need the diffusion coefficient for the concrete we are using. Here I have used H factor of 0.4. It could be a little bit higher, it could be lower. And here you see the distribution, the log normal distribution found in the quay structure. And also here I have added some characteristic values to show what is the effect of have different values of the critical chloride content on the service life achieved. And we often use 10% probability of corrosion, which is the serviceability limit state criteria for the acceptance of corrosion initiation. So some results. Here we are showing the probability of corrosion here versus the needed concrete cover to achieve 50 years service life. Here is shown from 0 to 1. It could be 0 to 100%, but here 0 to 1. Here is the calculated curves for the log normal distribution of critical chloride content, and also a fixed value. And you can see that this fixed value of 0.67 is very close to the normal distribution. And also this 0.34 is given here. And as we see, just for the mean value is 50%, so you can see here. But for 10% probability of corrosion, which is the acceptance criteria, we see that for the log normal distribution found in the concrete quay, and for this fixed value, 0.67, we need around 73 millimeter concrete cover to reach 50 years service life. But if we have a fixed value of 0.34, which is, let us say 0.4, then you'll see we need 92 millimeters to reach 50 years service life. That's a 20 millimeters in difference of concrete cover. So a new calculation where the service life is anticipated to be 100 years. We see that the concrete cover need to be increased. So for those two situations, we need 90 millimeter. As you remember, it was 73 for 50 years. Now you need 90 millimeter to reach 100 years. And for this low value of critical chloride content, this line here, you need 140 millimeter. But as you remember, from the last picture, this 90 millimeter, then you achieve 50 years service life, 4.34. So this result shows that the value used for the critical chloride content is very important, very sensitive for the obtained service life or for the needed concrete cover. So to sum up, or to have some concluding remarks, the critical chloride content secret is not clearly defined. As we have discussed or said, it's dependent on the definition. Is it the point where you have a kind of depassivation, or do you accept some kind of limited corrosion of the surface? And of course, in addition to material and environmental factor, if you are testing structures in the real field and the real structure or the lab, the results will be different, but also how the measuring method are, which measuring method are used, or how you interpret the test data. It's important. So you can have different results depending on how you interpret the results. And as calculation showed, this parameter Ccrit is a very sensitive parameter for the service life calculation. It's very important. And as I showed, the service life increases from 50 to 100 years if the characteristic value of Ccrit increases from 0.34 or say 0.4 to 0.67. And depending on this definition of the limit state onset of corrosion, both threshold values are realistic. The lowest value may correspond to the definition chloride content required for depassivation of the reinforcement surface, whereas the highest value may correspond to the definition chloride content associated with some surface corrosion of the reinforcement. So that's some of what I want to tell about the results from existing structure and the implication of the value of the Ccrit in service life calculations. So thank you for your attention. And I was asked for presenting the test results, and I added this calculation. So given an extra boost that we need good and reliable critical chloride content, and that's too conservative, because then in this sustainable days we should not need too high concrete cover if we not it's not correct, but we should not have too less either. So thank you.
Thank you for your interesting presentation. I think that there is time just for one quick question from the others. Okay, Frank, please.
I was interested in your graph, which linked chloride content and amount of corrosion. And then you suggest that critical chloride will depend on what your criteria is. But for me, that graph will show that the longer you leave it, the more corrosion you have and the more chloride you have, but they might be totally independent. The amount of corrosion will depend on the moisture content and resistivity, not on the chloride content. And so really you could set up a totally arbitrary critical chloride content because of that. And really it takes me back to, well, you need to have a critical chloride content which is based on when the steel becomes active, and then everything else is based on the propagation period.
Yeah, but maybe.
Yeah, I agree, maybe.
Yeah, it's very complicated. So I want to raise questions about how we treat it, and if we include some of the discussion is how much of the kind of propagation we are including in the first phase.
Yeah, well, that's right. There may be two propagation periods.
Yeah,
one where
maybe.
it's very, very slow, and then it speeds up, and that's a different one.
Yeah.
There is also a question in the from the chat from Elsener. I don't know if we have time to reply to this question right now, or if it's better to postpone this at the end of the presentation to discuss even on this issue. So maybe you can answer to this question by writing the answer, and then we can see it again together in the concluding remarks of the webinar, if you agree, or if you want to give a quick question right now, so all the audience can see the question. If you want to give a quick answer now, and then we can go into
the question was, thank you for the presentation. I wonder in which way the environmental condition, relative humidity, cyclic exposure, immersion conditions are taken into account in the service life modeling. And then it's not taken into account the local situation in the service life calculations. Is only the parameter I showed.
Okay.
Yeah.
Thank you.